The moon formed 4.5 billion years ago, some 60 million years after the origin of the solar system. Several forming mechanisms have been proposed, including the fission of the moon from Earth's crust through centrifugal force, which would require too great an initial rotation rate of Earth. The gravitational capture of a preformed moon, which would require an unfeasible extended atmosphere of Earth to dissipate the energy of the passing moon. And the cold formation of Earth and the moon together in the primordial accretion disk, which does not explain the depletion of metals in the moon. These hypotheses also cannot account for the high angular momentum of the Earth-Moon system. The prevailing hypothesis is that the Earth-Moon system formed after a giant impact of a Mars-sized body named Theia with the proto-Earth. The impact blasted material into Earth's orbit, and then the material accreted and formed the moon. The moon's far side has a crust that is 50 kilometers, 31 miles, thicker than that of the near side. This is thought to be because the moon fused from two different bodies. This hypothesis, although not perfect, perhaps best explains the evidence. 18 months prior to an October 1984 conference on lunar origins, Bill Hartman, Roger Phillips, and Jeff Taylor challenged fellow lunar scientists, "You have 18 months. Go back to your Apollo data, go back to your computer, do whatever you have to, but make up your mind. Don't come to our conference unless you have something to say about the moon's birth." At the 1984 conference at Kona, Hawaii, the giant impact hypothesis emerged as the most consensual theory. Before the conference, there were partisans of the three traditional theories, plus a few people who were starting to take the giant impact seriously. And there was a huge apathetic middle who didn't think the debate would ever be resolved. Afterward, there were essentially only two groups, the giant impact camp and the agnostics. Giant impacts are thought to have been common in the early solar system. Computer simulations of giant impacts have produced results that are consistent with the mass of the lunar core and the angular momentum of the Earth-Moon system. These simulations also show that most of the moon derived from the impactor rather than the proto-Earth. However, more recent simulations suggest a larger fraction of the moon derived from the proto-Earth. Other bodies of the inner solar system, such as Mars and Vesta, have, according to meteorites from them, very different oxygen and tungsten isotopic compositions compared to Earth. However, Earth and the Moon have nearly identical isotopic compositions. The isotopic equalization of the Earth-Moon system might be explained by post-impact mixing of the vaporized material that formed the two, although this is debated. The impact released a lot of energy, and then the released material reaccreted into the Earth-Moon system. This would have melted the outer shell of Earth and thus formed a magma ocean. Similarly, the newly formed moon would also have been affected and had its own lunar magma ocean. Its depth is estimated from about 500 kilometers, 300 miles, to 1,737 kilometers, 1,079 miles. While the giant impact hypothesis might explain many lines of evidence, some questions are still unresolved, most of which involve the moon's composition. In 2001, a team at the Carnegie Institute of Washington reported the most precise measurement of the isotopic signatures of lunar rocks. The rocks from the Apollo program had the same isotopic signature as rocks from Earth, differing from almost all other bodies in the solar system. This observation was unexpected because most of the material that formed the moon was thought to come from Theia, and it was announced in 2007 that there was less than a 1% chance that Theia and Earth had identical isotopic signatures. The Apollo lunar samples had in 2012 the same titanium isotopes composition as Earth, which conflicts with what is expected if the moon formed far from Earth or is derived from Theia. These discrepancies may be explained by variations of the giant impact hypothesis.